Good afternoon, good morning, and today we are going to talk about displacement current, and then we are going to finalize our Maxwell's equation. In the last class, we did talk about four laws. The first one was the Gauss's law, and before that, I did tell you about the divergence and the Stokes theorem that you should know. So we have the Gauss's law, and then we talked about Ampere's law, and then we talked about Faraday's law. We have written the integral and differential form of both Gauss's law and Faraday's law. Today, first we are going to discuss about the concept of displacement current, and after that we are going to modify the Ampere's law and going to write down a new equation and write down the differential and integral form of the same. So what exactly do we mean by displacement current? Well, we really start with that. Okay, in general, if you are basically considering any kind of conductor, you basically have uh, electrons which will actually flow through this conductor, right? So you basically have the electrons like this, and the electrons will always flow from the negative end towards the positive end. So the electrons will flow in this particular direction, and that's why we basically call it as the electronic current. But as a matter of fact, the current, which is actually the conduction current, will always be opposite to the flow of electrons. So this is something, a concept that we already know about. Okay, so here what I mean by I is actually the conduction current. So if I say that a current is flowing through a conductor, at any point I can actually find out the magnetic field. Now let's slightly modify this situation, and let's say in this current carrying conductor we are placing a capacitor in between. So a capacitor will basically have a positive plate, okay, and this would be your negative plate. You are applying a AC source, and in between there will be an electric field, and of course there is some dielectric material. Now the current which is actually flowing through the wire, this same current cannot flow through this because this space is more or less empty or has a dielectric in between. A dielectric, you can consider it as an insulator to a certain extent, so the current cannot flow. But what happens is that in that case, if I basically measure the magnetic field here, this should more or less be zero. Okay, so that's important. But if that happens, that means that the Ampere circuital law is partially true. It is true for this circuit, but this is not true in this particular case. Okay, so by Ampere circuital law, if we just write down the straightforward Ampere circuital law that we have seen in the last class, if I write down Ampere circuital law as B dot dl is equal to mu naught I, okay, mu naught I, this I is actually the current enclosed. Now in this particular case there is no current enclosed, okay, and if there is no current enclosed, then this integration of B dot dl should be equal to 0. That should be the case, okay, for this particular scenario. But this is not actually true. It is observed that this is actually not equal to 0. That means there is obviously a certain magnetic field that is there. So that means there is a current, but that may not be this conduction current. It has to be something else. Okay, so what happened is this is actually called the displacement current. Okay, and this current is because of the changing electric field. Okay, the changing electric field. So if you really want to write down this, we can say that this is my situation 1 and this is my second situation. Okay, and if someone asks you to explain displacement current, you can say that in the the second situation, in the second situation, okay, the enclosed current is 0, right? Enclosed current is equal to 0, correct? But integration of B dot dl is not equal to 0. So that means there has to be certain current. Okay, so in that way we can say, hence, okay, when we are talking about the Ampere's law, hence Ampere's law, which we have written just now, Ampere's law needs to be modified. We have to basically modify it, needs to be modified. So what we are going to do now is we are going to modify this Ampere's law so that this is true for both the cases. Okay. And before we really start, let me just give you a gist of what exactly we are actually going to derive or show. So let me just write down the topic or the equation of that. Modified Ampere's law. Modified Ampere's law. And how does modified Ampere's law look like? If we write down the modified Ampere's law, this is something which you again have to remember because this is a part of the Maxwell's equation. The left hand side will remain the same. B bar dot dl bar is equal to, well, the first term is not an issue. This is mu naught I. Okay. Plus we have to take an additional term which will include the uh, displacement current term. We are going to look into that later, but let me write down the final equation. Mu naught epsilon naught d phi E. Okay. Here E basically stands for the electric field dt. So, phi is usually the notation for flux. So this is my modified Ampere's law. So please remember this. This is important, and this is something which we are going to derive now. Okay. So let's do it. Okay. So I basically have got two regions here. I'm not going to redraw the figure. Let me just take the sim figure here. Okay. Let me say this is my region 1 and this is my region 2. Okay. This is my region 2. Okay. So if I do that, okay, if I take the region 2 and region 1 separately, I can find out the equation separately for both these regions. Okay. So in general, if I just want to explain you with this 3D diagram, you see there is a plate here. This is an electric field in between. This is a plate and the electric field is from up to down. So that means this is your positively charged plate and this is my negatively charged plate. The electric field goes from the positive plate towards the negative plate, right? So in that way, I can say this is my situation right now. So in the first case, what we are saying is for region 1. Okay, so let me just write down for conduction in region 1. For conduction in region 1. Okay, so if you consider the first region for conduction in the region 1, we know that the electric field is constant. There is no changing electric field. There is a constant current that flows through this region. Okay, so we can say the electric field, let me just write it down in this way. Electric field, okay, is constant. So if the electric field is constant, then we can simply say that d of phi e, right? Phi e is the nothing but the magnetic flux dt is equal to 0, right? Because we have seen in the last class and obviously you know it as well. The magnetic flux is equal to nothing but E dot A. But area is constant. E is the electric field and I am saying that the electric field is constant in this region where there is no capacitor. So that means d phi E dt is equal to 0. Okay. So that is the first scenario. So in that case, if really replace this in this particular equation, we can simply say that integration of b bar dot dl bar, okay, is equal to mu naught I, because this part is 0, right? So there is no issues in that. Okay, so we can write it like this. Okay, now in the second situation we have got the region 2. Okay, so let me take number 2. Let me take number 2 and let's talk about the second scenario. Okay, so in second scenario we can say it is for region 2. So which is our region 2? This is our region 2, right? In between the capaciting plates, okay? In between the plates, okay? In region 2. So we can say in region 2, the field between the plates, okay? Let me just write this down. The field between the plates. So what can I do here is that in general, if you're if you remember your lower classes, the electric field between two parallel plate is nothing but E is equal to sigma divided by epsilon naught. What is sigma? Sigma is the charge density. Okay, in fact it is the charge density per unit area, or the charge per unit area, right? So we can say it is nothing but Q divided by A epsilon naught. So I can write it like this. Okay, please remember this: sigma is equal to Q divided by A. You might have done it in your lower classes, so this is a result that you should actually remember. Okay, and this is something which we call as the surface charge density. This is our surface charge density. So there are obviously certain results that you should actually remember in order to solve such problems. Okay, now we can actually find out what is the flux. We are trying to prove that the second term is actually a part of current. Okay, so if I want to find out the flux, I can simply say phi E. The flux due to the electric field is nothing but E bar dot A bar. Okay, and just now we said that E is nothing but Q divided by A epsilon naught into A bar, right? So let's just cancel this area out, and then I will be just left out with Q divided by epsilon naught. Okay, so what we can do here is, okay, if you just look into this part of the equation, only this part of the equation, let's try to write down this equation here. We can say that epsilon naught, okay, d phi E by dt is equal to, okay, now d phi E by dt, we can do it, right, because we know what is phi. So I can take it as epsilon naught d dt of phi. Phi is q by epsilon naught. We have just now seen this. So we can write it down as q divided by epsilon naught. Now this epsilon is a constant, so I can just cancel it out. So I've got just dq divided by dt. Now what is dq by dt? dq by dt is nothing but current, right? But this current is because of the electric field. So let me just write it down as id. Okay, this is written as id. Okay, so in general, if I just multiply mu naught on both sides, I can simply write it down as mu naught epsilon naught d phi E divided by dt is equal to this side multiplied by mu naught. So this side also I can multiply it by mu naught into id. Okay, now this id that we actually have here is actually called the displacement current. So this is the most important part here. We have found out what is displacement current. Displacement current. So at first instant you might say that how can this be current? But if we find out the flux, we get it to be epsilon I q by epsilon naught. That epsilon naught gets cancelled. So I get dq by dt, and dq by dt means rate of flow of charge. So that has to be current. So this is the displacement current, which is actually due to electric field. Due to electric field. The sole reason for this displacement current is actually electric field. Okay, so this is important. So that means we have proved that this is our electric field. So again, if we are considering this equation, we can simply say that integration of b bar dot dl bar is equal to the first term, which is actually nothing but mu naught I, is actually 0 because it does not have any current, or we can say it does not have any kind of conduction current. Okay, it simply has the displacement current. So we can just write it down as mu naught epsilon naught, okay, d phi E by dt. Okay, d phi E divided by dt. Okay, so this one we can actually write it down as mu naught into I d. So in that way we can actually have the modified Ampere's law. Okay, and the modified Ampere's law is, therefore we can simply write down in totality b bar dot dl bar is equal to mu naught, obviously, and we have two currents here. First is I, the conduction current, plus I, d the displacement current. A good thing to note here is that this is actually one form which you can write down, but when you write down for your exam purpose the Maxwell's equation, you should actually write down this detailed expression. This is more important. Okay, anyway, we are going to list that down later, but this is how you actually show what is the current here. Okay, so obviously the leveling is important. You should always write down what are the different terms here, as I've said verbally, but let me just try to write it down. Okay, this I is called as the conduction current. Okay, and id is the displacement current. So in this way we can actually understand and explain displacement current. Okay, discussed four different laws, in fact three, but we can actually say about the fourth one as well. We have talked about Gauss's law in electrostatics, Faraday's law, and the Ampere's law. We've also looked into the fact that the Ampere's law actually can be modified, and we can actually write it as the modified Ampere's law. Now what Maxwell did in the year 1865, he actually has combined all those four laws and stated them together, which actually forms the backbone of the electromagnetic theory. So what we are going to do now is we are going to list down all these four formulas, and we are going to look into the final form of the Maxwell's equation. So for that I'm going to take up two parts, because depending on your question you might basically get a question where you are supposed to write down the integral form or the differential form. So let's try to write down both of them. Okay, so on one side let me just list down the integral form of Maxwell's equation, and on the other side I'm going to write down the differential form. Although we have derived all four of them, all the forms we have already derived, so just going to look into them one by one. So the very first law that we have actually talked about is the Gauss's law, and in fact we are talking about electric field here, so this is actually the Gauss's law in electrostatics. So I will just take it to be E bar dot if you can recall this is ds bar is equal to 1 by epsilon naught times the charge enclosed. So I'll write it down as q divided by epsilon naught. Okay, so this was my Gauss's law in electrostatics. Okay, Gauss's law in electrostatics. So this is the first form that we have seen. Okay, but at the same time this Gauss's law in electrostatics can also be written in the differential form, and for writing it down in the differential form I can write it down like this: del bar dot E bar is equal to rho divided by epsilon naught. We have also seen what are the different forms here, what is rho, what is q, and so on. Okay, but anyway I'm going to list that down at the end, but at this point of time we should actually remember what are these values. So this is my differential form of Gauss's law. In the next thing would be the second law that we are going to talk about is the Gauss's law in magnetostatics. So what happens is, if you are having an electric field, you can also have a magnetic field and find out what is its equivalent equation. So B bar dot ds bar is equal to 0. Now this side it's 0. This is called the Gauss's law in magnetostatics. So this is again important. So I will write it down as Gauss's law in magnetostatics. So whenever we are talking about the magnetic field, we are going to talk about this law. So this is the integral form, and the differential form is also something which is similar, and we can write it down as del bar dot b bar is equal to 0. Okay, so that's the differential form of Maxwell's equation. The third case would be Faraday's law, and if you recall we have written the integral form first, and the integral form was E bar dot dl bar is equal to minus, where minus actually comes because of the Lenz's law, d phi b dt. So Faraday's law gives you a direct connection between the electric field and the magnetic field here. Okay, so this is my Faraday's law. So I can simply write it down as the Faraday's law. Now, if you're talking about the Faraday's law, again, this will also have a differential form, and the differential form of Faraday's law, as we have seen, we have used the Stokes theorem for finding out that. Okay, you can just go back to the previous lecture and check that. Del cross E is equal to minus of del B divided by del T. Okay, or you can write it down as dB by dt. Okay, the minus sign will be there. So minus sign is important when you are stating Faraday's law, so please don't miss that out. Okay, and the fourth one, which is actually the Ampere's law, was actually in fact modified by Maxwell, and he actually has given the concept of displacement current here, and we can write down this modified law as the fourth expression. So the fourth expression is B bar dot dl is equal to mu naught I. That's the expression because of the conduction current, and if you're looking into the displacement current, it would be mu naught epsilon naught d phi. This is because of the electric field dt. So the displacement current is because of the electric field. Okay, and this one we are going to write it down as modified Ampere's law. Okay, modified Ampere's law. So this also has our differential form. Okay, and the differential form for this is, you can write it down in two ways. Let me just write down the first form. You can get it in books in different forms, but for exam purpose you can just remember one of the form. Del cross B, okay, that was actually dot dl. Now we are talking about the curl. Del cross B is equal to mu naught J, okay, plus mu naught del D del T. Okay, so we have seen the expression, okay, and how exactly we actually get this. Okay, so we can either write it down like this, or we can also write it down like this. Del cross H is equal to J bar plus del D del T. Okay, you should not get more or less confused here, because it's simple. What happens here is two things that you should actually remember here. Okay, that what is my D. Okay, if you talk about D is actually nothing but epsilon naught E. So if D is epsilon naught E, you can replace it here. That epsilon naught can come out and you will get del E del T. Mu naught epsilon naught del E del T. Mu naught epsilon naught del E del T, right? So get this expression. So if you modify it and you take it in the differential form, you're going to get this expression. In place of phi E, it will be E. Okay. In a similar way, if we write down H, okay, see, if you divide this by mu naught, and this side also you divide by mu naught, that means that my H is equal to B by mu naught. Please remember this expression. This also is something which you might have seen before. B is equal to mu naught H. Okay, so before I go into the different terms that are involved here, let me just give you a very brief idea about the Gauss's law in magnetostatics. So in Gauss's law in magnetostatics, we are saying that closed integration of B bar dot ds, okay, closed integration of B bar dot ds, okay, is equal to 0. Okay, so what does it stand for? Whenever we are basically saying it's a closed integral, that means it's basically, if you're talking about the field lines in case of magnetic field, let's say this is north and this is south, the field lines will always go from north to south. So if you are basically talking about the field lines, and if you want it to be closed, that means it can start from the north pole, no doubt, but it should end at the south pole. So in simple words, we can say that the magnetic monopoles don't exist, because if there is only a north pole and there is no south pole, the field lines won't get closed, as a result of which we can just say that we have a dipole system, because for a monopole we are not going to get a closed integral. So this is important. So this is a result because of which we can simply say this result says that magnetic monopole does not exist. Okay, so a conclusion to this is magnetic monopole, okay, monopole does not exist. Okay, there is no such thing as a magnetic monopole. There will always be a dipole. Okay, so having talked about these Maxwell's equation, let me just write down what are the different terms here. In exam purpose, if you are asked a question on write down the Maxwell's equation in differential form or integral form or both, you have to obviously explain what are the different terms here. Okay, so for that, after you write down all the expression, please make sure that you mention these terms. Okay, first term is d. Okay, let me take d, begin with d. This is nothing but the displacement density. Okay, this is basically called as the displacement density. This is actually connected with the electric field, and I term it as displacement density. Okay, and as I said, displacement density is equal to nothing but epsilon naught times permittivity of free space times the electric field. Okay, so that's the displacement density. That's the first thing. And then we have come across rho here. Okay, if we look into the Gaussian law here, rho. Okay, this rho is called the volume charge density. You might have come across in your lower classes as well. This is called the volume charge density. Okay, charge per unit volume. Okay, that's the second term. The third one, which is B, let's take B and H. We can talk this as the magnetic flux density. Okay, B, I will write it down as magnetic flux density. The fourth term is H, okay, because we connected B and H, and I said you can write down either B or H, okay, whichever form you remember. This is called the magnetic field density. Magnetic field density. So you can write down your expression in terms of B or H, plus please remember that you are writing down the correct expression. That is very important. Okay, so the relation between magnetic field and flux density and magnetic flux density is B is equal to mu naught H. Okay, and this is what I have replaced here, and I have got the equation in two forms. You can write down any of the form. If you check any book, consult any standard book, you can get any of the forms. Okay, one of the form you should remember, that's important. Okay, and then we have got E, which is the electric field. Okay, and then finally J. So J also is a term which you might have come across before if you remember something which we call as current density. This is my J. Okay, so this is actually the current density. Okay, this is also there in your lower classes. This is important as well. Okay, drift velocity concept and all these things, it can be used there as well. Okay, current density. So current density means J is equal to current per unit area. So J is equal to I divided by A. So this is the way to remember this. So this is important. Okay, now what we have is 4 equations, and these equations are valid when you are basically having a free space. Okay, free space in the sense that you basically have some kind of medium, not a free space, sorry, you have some kind of medium. Now if you have a free space, that means let's say a vacuum. Okay, so what happens is some of the terms, for example, if it's vacuum, we won't be getting any kind of volume charge density. Okay, or the volume charge density won't be there. Okay, and then the current density won't be there, and so on. So there can be one more question which comes up, is write down the Maxwell's equation in free space. Okay, so in free space, so for in free space it's very simple. You have to just remember those expressions, that's it. And for free space you have to just remember certain additional points. Okay, in free space this J is 0. Okay, that's the current density. It will become 0 because there is no current in free space, so it is I by A, I is 0, so that's 0. Okay, similarly the volume charge density, there will be no volume flowing in free space in vacuum. Okay, so rho is equal to 0. We have already used epsilon naught there, so epsilon naught will be there. Okay, with this free space, and permeability of free space also, it is nothing but mu naught. And that way we can actually write down the modified Maxwell's equation here. Okay, by putting J and rho as 0, Maxwell's equation. So in free space the Maxwell's equation will become something like this. So the first expression in the differential form was, okay, let me just go up, it is del dot E is equal to rho by epsilon naught. So rho is 0, So the first expression would be del bar dot E bar is equal to 0, right? That's the first expression. The second one, it's already 0 on the left hand side, right hand side, so I'm not going to think about this much. This is del bar dot B bar is equal to 0. And then we have to take the cross term. Let's take about del cross. This also can be written in differential form and integral form. I'm just writing it down in the differential form. So you see del cross E is minus del B del T. So there is no J, there is no rho. So this Faraday's law is not going to change much. So it will be remaining as minus of del B divided by del T. And finally, the fourth expression, we have it as, okay, let's check this. Look into the modified equation. Here we have J, so this part will become 0 and then the remaining part will remain as it is. Okay, so for the fourth expression, I can simply write it down in terms of B or H. Let me write it down in terms of B. Del bar cross B bar is equal to mu naught del D by del T. That's it. Okay, so this will be the Maxwell's equation in free space. For example, Maxwell's equation integral form, Maxwell's equation differential form, and Maxwell's equation in free space. So if you remember these two, for free space it's not a problem, just replace rho with 0 and J with 0, everything else will remain the same.